So let's go ahead and get started. Hi, my name is Brian Hall. I'm a VP of Operations for Expiro. On the call today is Ted Wilmes, who's going to walk you through some content that we've prepared called Graph for SQL People. Let me start off by saying a little bit about Expiro. We typically consider ourselves as product ideation consultants. We help bring complex products to life. What that tends to mean for our customers is that we tend to need to surround them with some mixture of product strategy, support, user experience, and architecture and development. We're organized as a consultancy around these three specialties, and typically what we do is try to surround a domain expert with whatever support they may need. It could be a basin modeler in the oil and gas business, could be a bond trader in finance, or it could be a geneticist in a biotech scenario. Frequently, these guys in the middle, they're specialties in their business, but they don't realize it, but they're also in the software business. So oftentimes they don't know what a roadmap should look like. They don't tend to know what graph databases are or what a proper user experience might require. So what we do is we bring that support to the domain expert to whatever extent they might need. I'm going to mute. Let's see. I'm going to mute a few of you, getting some background noise. Okay. Next slide. Expiro's been in business 15 years. We have a lengthy list of happy customers and a growing list of partners that we do business with. A couple of them are listed at the bottom that are particularly germane to the graph topic today. So without further ado, I'll hand it over to Ted.
Hey everybody, so as Brian mentioned, my name is Ted Wilmes. I'm a data architect for Expiro. I personally have a fair amount of relational database and graph experience, so I say that in particular because I'd like to really give an even-handed overview of the graph landscape today, and this isn't really meant to be a SQL versus graph discussion, but more of a just discussion of, if you're interested in graph, kind of how do you map some of your SQL knowledge over to the graph world. If the spirit so moves you, I've been told by our wonderful social networking people that you can tweet this presentation out with the hashtag SQL to graph, but I admit I am a social networking noob, so I will leave that up to y'all. So what are we going to talk about today? First, overview of the graph landscape, and then the focus of the presentation really is going to be on Apache TinkerPop. So I'll talk about the Apache TinkerPop ecosystem. We'll talk about the property graph model, and then go into some specifics about graph-related things. So graph indexing and constraints, graph queries, so you'll see some side-by-side queries in the SQL and the graph world, and then finish up with a discussion of graph analytics with Gremlin and the SparkGraphComputer, which is one implementation where you can run large graph jobs on your Spark clusters. That's some pretty interesting stuff. We'll finish up with that. So as I mentioned, there's a ton of folks out there, obviously, with relational database experience. That's how I got started. That's how a lot of people get started. There are still many, many use cases where an RDBMS is the way to go. But at the same time, there's been graph databases around in various forms for a while, and they're starting to gain some more popularity in certain areas. In certain areas, they've been around and already in a fair amount of use. But what I'd like to do today is to give you a little bit of a baseline that you can start exploring Apache TinkerPop from, and use the relational world as kind of a jumping off point for comparison, just because that's something that folks are familiar with. One thing that comes up a lot, of course, is kind of folks wondering when it is a good idea to use or to maybe use a graph database versus another NoSQL database or a relational database. I'm not going to directly touch on that today, but if you are interested, Josh Perryman and Sebastian Good, some other Expiro folks, did a really excellent presentation a little while ago. We have the link here. You could go check it out. It gives a very even-handed, I think, overview of a number of different graph databases, but then also deals with some of the nuances that may be required to come up in the decision if you're making a decision about one store versus another. So we like to think that we take a very pragmatic approach to that sort of decision and try not to be too religious about it. Okay, so the graph world. So today we're going to talk about databases that are primarily following this property graph model. But previous to that, of course, there's been RDF and triple stores around for many, many years. And so I've listed a few vendors on each side just to give you guys some names you could go look up if you were interested. There's a few RDF triple stores that actually provide a property graph mapping, so you're going to see logos on both sides in that case. Triple stores are sometimes thought of as being more analytical type databases versus transactional, but in fact there are a fair number of deployments out there where these are being used for low latency transactional type scenarios. So that's not necessarily true that they're kind of just boutique esoteric things that are used for analytical processing. And as I mentioned, they've been around for many years, and this is not an exhaustive list, but you can just kind of use this as a jumping off point. So specifically in the property graph world, today I'm going to be talking about Apache TinkerPop. And there's a number of vendors or graph providers that implement the Apache TinkerPop interfaces. And so you'll see there we have Neo4j, BlazeGraph, Stardog, OrientDB, Titan, and then DataStax is going to be releasing a graph database, DSE Graph. There is also, I'm sure you've heard of Neo4j, another great graph database implementation. They have their own query language called Cypher, and there is a project they started called OpenCypher, I think about a year or so ago. Right now, Neo4j is the only company I know that is supporting the Cypher language, but I know they had a number of other partners that were working on also implementing Cypher into their solutions. So you can check out the OpenCypher website if you're kind of interested in what the progress of that is. Now, again, Neo4j is listed on both sides here because you can also access it with the Apache TinkerPop tools. And then I also have OrientDB on here because they've also come up with their own kind of SQL type variant, which allows you to run graph queries against their system. And again, they also implement the TinkerPop interfaces. So what is Apache TinkerPop? So Apache TinkerPop is a project in incubation currently with the Apache Foundation. It's a graph computing framework. And so it supports both OLTP and OLAP graph processing. I'll kind of define later on what I mean by OLAP in the graph world. But it provides both of those. And it works with a continuously growing list of different graph providers. So I've listed some already in this presentation, but new graph providers are coming on and adding TinkerPop support into their systems. Now, I should say it's not specifically a language standard. So even though Apache TinkerPop has a language associated with it, which is Gremlin, it's not just a, say, standards document that other folks are going out and, say, implementing their own version of SQL with their own query optimizers and all those other pieces. The TinkerPop project itself comes with an extensive graph computing engine in it that providers can plug their data stores into. And then they can kind of choose which portions of the graph processing that they want to implement themselves versus use what's built into Apache TinkerPop. Along with this, TinkerPop provides a server so you can have remote access to your graph database, Java-based Gremlin driver, that's the client side of that access. a vertex-centered computing implementation that falls in line with the OLAP processing. It also has its own graph that it comes with called TinkerGraph, which is an in-memory graph. And there's various other bits and pieces that make up a really robust graph framework solution. Okay, so now for the TinkerPop to SQL side-by-side comparison here. So this is kind of what I like to think of as that mapping between the two worlds. So on the left, on the SQL side, and then on the right, you'll see the graph side. So connectivity-wise, in the SQL world, we have things like ODBC and JDBC. On the graph side, specifically, again, when I say graph, I'm just talking about Apache TinkerPop here. It's different for the other sorts of graph tools. But for TinkerPop, we have Gremlin drivers that are connecting to the Gremlin server. The project, TinkerPop project itself, has a Java, Scala, PHP, or excuse me, a Java driver. But then folks have implemented other drivers. So there's a Scala, a PHP, and a Python library also. So that list is also being continuously added to and expanded out. Language-wise in SQL, well, that's probably pretty obvious here. It's SQL. On the graph side, we have Gremlin, like I mentioned. Management of these different databases, this is where it gets more vendor-specific, which is really exactly the same in the relational database world. So if you're using Postgres, you're going to use Postgres admin. SQL Server, you're going to use the Management Studio. On the graph side, it's going to depend on who your graph vendor is. So say if you were using Titan against a Cassandra backend or possibly DSC Graph, then you're probably going to use Ops Center. If you're using Neo4j, you're going to use their management tools. So TinkerPop doesn't pull the management pieces into itself. Bulk import and export, again, some of these things will be vendor specific. On the TinkerPop side, though, there is a standard bulk loader and bulk dumper vertex program, it's called, which allow you to, in the standard Apache TinkerPop way, pull data into your graph and then export data out of your graph. On the visualization side, this is one spot where I have a coworker that likes to say that the graph landscape is kind of in its teenage years right now, and so we're still building up our list of third-party tools that can interact with these different graph databases. So if you think of visualization or business intelligence, there's a load of options on the relational database side. On the graph side, the list is smaller, but it's growing. So you have things like keylines and limcurious, different ways to visually interact with your graph data, move through it, and do different sorts of reporting and analytics off of it. Okay, so here is a very simple relational database diagram that you guys are all probably very familiar with. The data that we're going to use today, just as our little example, is based upon a simple demo that we have in-house where we have manufacturers own factories. Factories make batches of things so they can make parts or sensors. Maintenance is performed on these parts, so pretty straightforward set of relationships here. So what we're going to do now is kind of map this over into the property graph world. So the property graph, what do I mean? I've said property graph model a few times here. So when somebody says triple store or RDF, they mean one particular type of model. When I say property graph model, what I mean is we have these basic components of vertices and edges. And so you can see two vertices here and then an edge connecting them. Now, the property part of this comes from the fact that the vertices can have properties. So on the left, you'll see there's a name property. They also, in the TinkerPop world, can be labels. So the label, you could think of it as kind of like a typing. And so we have a label of manufacturer on the left and a label of factory on the right. So the manufacturer owns a factory. The edges are also labeled, and in many cases you'll find that those labels will be a verb. So you say a manufacturer owns a factory. And like with the vertices, the edges can have properties. So in this case, the property is the fact that the manufacturer bought this factory in 1997. Now, those properties can be various data types. They could be simple strings, doubles, integers, whatever it may be, or something more complex. Some of it is vendor specific though. Okay, so now to break down our relational model. So if you were thinking, okay, I've had this relational model, I'm interested in moving it over to graph, or what would that look like in graph? We'll talk about some basic ways that you could look at that here. So here we have our manufacturer and there's a factory. So there's going to be one manufacturer and it's going to have an association with probably more than one factory, owning more than one factory. And so on the right over here, you'll see we have that manufacturer. This is the same as the previous slide. It owns a factory. So that's pretty straightforward. You just add an edge between the two. Now if we want to look at a many-to-many, if we look at a relational model, we have our many-to-many example is we have maintenance being performed on parts. So a particular maintenance activity could encompass more than one part. And then at the same time, through the lifetime of a part may be associated with more than one maintenance activity. For example, if that part had maintenance performed on it more than one time. So one way to do this is, again, it looks very similar to the previous slide. We just add an edge between our maintenance activity vertex and then our part vertex. And you can associate the different properties and then use them while you're querying or pulling data back for any sort of analysis that you want to do. Now, another alternative thing that you sometimes run into when you're looking at modeling in the graph databases, when should something be an edge versus pulled out as a vertex? And so here I have a little example here. I have my two cats here communicating over email. It's a pretty realistic example. So we have Isabel is sending an email to Ricky. So in this case, we've modeled that as an edge. So we have this emails edge with some content on it. Well, that might support certain use cases. Say you're asking, okay, who did this particular user email? Okay, well that can support that use case fine. That's an easy query to do. One other thing you could do though is actually go in and pull that email up into its own vertex. And so now we have the user, and then there's an email vertex itself. You could associate other things with that vertex. Maybe it would have other edges going out to it. For example, if you were tagging all the emails with certain tags so that you could go back and do some sort of analysis based upon those tags, it may be better to actually pull that out into its own top level vertex. So long story short here, really there's a lot of flexibility, and you can, when you start your modeling, especially if you're moving from your relational database into your graph database, it helps, just like in any data modeling exercise, to think about what sort of queries am I going to be running on this data after I get done with this. And that'll help inform a number of your modeling decisions, deciding when something should be an edge or a vertex. That becomes a lot more obvious if you start thinking about, you know, the things that you're going to be doing with the data after you've moved it into this graph structure. Okay, so now if we pull out back a little bit and we look at our graph schema, I kind of think of graph schema usually as a kind of a schema by example. A lot of times when you end up documenting your graph schema, you just really end up drawing out some portion of your graph as your form of documentation. It's not like in the relational database where you might dump out all of your, say, DDL statements or something like that. So here we have, it looks very similar, but we have our manufacturers. There's two listed here because, again, it's a schema by example. It's not just one single instance of the manufacturer. Schema, the manufacturer owns a factory. Trucks are made in factories. I won't read the whole thing back to you. You guys can read, I'm sure. But that's the basic idea. Okay. So now we'll get into the data definition language pieces. So if I'm creating this, so this is, of course, you've seen this 1,000 times. Either you've written this out or maybe a tool that you've used has generated this. And so in SQL, this would be how one would create a table. Say, create this table, here's the columns, there's some typing information, maybe some other constraints that you're putting in there, like a column can't be null, things like that. I'm going to use Titan for these examples. This is a spot where this is vendor specific. And so we'll just use a Titan example here. In Titan, you would log in and there's a management interface. And so when you have an instance of this management interface, there's a few things that you can do schema-wise. You can create vertex labels. So here we're making a vertex label manufacturer. You can add properties, so vertex and edge properties, and when you define a property, you define the property name, so this property key here, and then a data type. So I'm going to say the name is a string, and then you can also define what the cardinality is. So is it going to be a single value, a set of values? You have some flexibility there. Then we'll create an edge label. This edge label, like you saw before, we're creating this owns edge. And so basically, this is kind of at the level that you define these schema elements. There isn't a way in any of the current property graph databases that I'm familiar with where you can do something like say, okay, well, I have this manufacturer, but the manufacturer is only going to have, these 4 properties, say like a name and then a date that they were founded. It's not like the relational database in that way, and that you can define things to that level. There's nothing to say that a graph database vendor won't add that at some point, but it's just currently that is something that I haven't seen supported out of the box. So somebody would have to define those constraints on their application side at this point. Now, edge labels, you can also do some constraints here, and so I'll talk about those next. So constraints, what I mean, in SQL world, we have primary key. You can say something's a foreign key, it's unique, non-null. There's various constraints that the different SQL providers allow you to use. On the Titan side, again, this is vendor specific. You can do things like define the multiplicity of a particular edge. And so you could say this owns edge is a one-to-many versus say a many-to-many. On the property side of this, you can do unique constraints. So you could say that this particular property key needs to be globally unique in the graph. So if you only want one particular user to have a certain username, you can say that that particular username property should be unique. Again, this is Titan 1.0 syntax here. If you were using DSE graph or another graph implementation, these bits would look different. This is where the different vendors can come in and kind of define how they're doing particular things versus TinkerPop saying, okay, this is how you should do it. When it comes to performance in relational databases, one thing that you'll commonly do is define different sorts of indexes. So in the graph world, there's the same thing. The indexes are a little different, of course, but there still is that need to index things. So there's 2 top level, I'll call them, types of indices. There's the global graph index, and then there's also vertex-centric indices. So for the global index, the way I think of it is we have this graph sitting out in front of us. And so we're going to run some particular query against this graph to pull some information out of it. And so for the global index, I need to, as efficiently as possible, figure out the set of vertices that I'm going to start my query with. I don't want to actually have to go through and hit all of the vertices in the whole graph. It may be a huge graph. I want to dive down into the ones that I'm particularly interested in. So that's where the global index comes into play. Now, if you were using something like DSE graph, then it's going to use DSE search to do that sort of initial global index lookup. And so then it'll efficiently be able to go in and grab that first set of indices. If you're using another vendor, they may have their own particular global indexing option. So some index under the covers that's allowing you to do that sort of lookup. The vertex-centric index is now you're in the graph running your query, but you're at a particular vertex or set of vertices, and you need to efficiently filter out and figure out what edges you should traverse for, say, that next step in your query. So if I'm at, say, this company vertex, we'll call it Acme. One word that you make here come up is this supernode. And a supernode is kind of defined as a vertex that is connected to many other vertices. And so in this case, we have this company and it has an employee's edge going out to some very large number of employees. And so one way to perform a query would be to actually go out and iterate through that full list of vertices that is connected to do if you're doing some sort of filter. So in this case, let's say we want to filter and only grab the employees that have been with our company for between 20 and 30 years. And so you could exhaustively go through and do a search and then get your results back. But of course, at a certain scale, that's going to become prohibitively expensive and time consuming. And so in this case, with a vertex-centric index, the graph provider will behind the scenes provide some sort of efficient indexing structure that lets you do queries on, say, years of service in an efficient manner so that you're only pulling back the edges that match your criteria that you're searching on. So now for some basic querying, so just some side-by-side graph, TinkerPop, and SQL comparisons. So one way to get started with TinkerPop, and I'll have some more links at the end so you guys can go check this out on your own, play with it, but one way to get started out with it is simply to interact through the Gremlin console. And so here's a little screenshot of the console. When you go in to the console, you'll see a number of plugins are activated. These are different pieces of functionality that you can add into the console, and then you can connect to a graph and start querying. So first, a Gremlin traversal. Most Gremlin traversals, if not all actually, start with a G. So that's going to be your graph traversal source. So think of that as the starting point of all your graph queries. Next, we're going to go and query against all of our vertices in our graph. And then following that, you're going to see a series of steps. These are the things that I'm going to be showing you next. And ultimately, these are in the OLTP world, these are going to be basically lazily evaluated. So you're going to be able to get an iterator and then iterate the results out from your query. So this is the very basic pattern that your Gremlin queries are going to follow. So let's start with actually adding data into our graph. So on the top, of course, we have our simple SQL statement where we're inserting data into a manufacturer table. Simply two columns there, we have a name and then the founded year. And so in the Gremlin world, you'll see that we have our G and there's an add V step, and then you provide a label. If you remember that earlier we could define a label, so we're adding a manufacturer and then setting two properties on it. Name, Acme Sensors, and then the founded year. So again, you can have various data types for your properties, as you can see here, and various properties associated with a single vertex. So now let's say we want to update that previously created vertex. So in SQL, you can simply do an update and then do a filter maybe on a particular primary key ID, and then set a column value. In Gremlin, similar sort of pattern here. We're going to grab, actually now you'll see the V here, and then we're going to look up a vertex ID. So let's say we know that that vertex's ID was 1. And then we'll set this property again, same step that you saw before that we used when we actually added the property to the new vertex. We're going to call this property step here and set founded to 1976. So now, since it's a graph, of course, graphs are all about creating and studying relationships between things. So what would be a foreign key in the relational world now becomes an edge in many cases in the graph world. And so I have two variants here for creating an edge between two vertices. So for the first one, we're looking up our vertex again with ID 1. Then we're going to do the add E step, so add an edge. The label there, owns, so this particular vertex owns vertex 2. Now this may look a little strange here, there's that next on the end of it, on that GV2, but that's because we're going to call next on that iterator that this graph traversal is providing. So it's kind of like we have this little sub-traversal nested within our E, add E step. The second variation is more verbose, but can be used quite easily within other Gremlin queries. So say you were maybe writing some sort of complex query that was doing a more complex traversal through your graph, and you were maybe associating certain pre-existing entities with each other. This would be how you could do that in that case. So in this case, we're adding a new step in here called this as. This as lets you alias particular parts of your traversal, kind of like in SQL, how you could say alias a particular column name and then refer to it with that column name in other spots in your query. So here we're grabbing vertex 0, aliasing it as A, and then vertex 1, aliasing it as B, and then our add E looks like the same step as before, but it's a little different here. We're just giving it the label and then defining a from and a to, and that connects those two vertices together. So now on the read side, really simple SQL query. Say we want all of the manufacturers, select star for manufacturers. That's about as easy as it gets. If we move over to Gremlin, we do a g.v, and now we're adding a has label. And so this has label is going to go and say, every vertex with this label manufacturer, I want to get that back. The default behavior is going to be that we'll get back these vertex objects themselves, and so you're seeing their toString here, which is just simply showing the vertex ID. So 1, 2, 3, 4, 5, 6. Now that's cool, but we probably want to see actually, okay, well, what properties are on those vertices? There's a value map step that returns, as you'd probably guess, a map from those vertice properties. So here we have a name and then the founded, and you can see that here listed just in a row. We have all of our different manufacturers. Those founded dates are totally made up, so don't fact check me on those. Now if we want to do a particular projection, so I just want the name for manufacturers, Gremlin, there's a values step. And so with this values step, we can provide one or more property names, and then we'll get those back. So here we just simply look up the names. Now what if I want to filter? So select name for manufacturers where name equals Volvo. So now we have our GV has label, so that's the same, but now we're appending another step on there, has name Volvo. So it has the property with the name Volvo. Then we're looking up just the name, so we just want the name back. Now this is one spot where, depending on the vendor implementation, say you were using DSE Graph or Titan, when you run this query, behind the scenes, the graph vendor has the ability to optimize this query and decide whether or not it can use an index. And so at the TinkerPop level, it doesn't know whether or not this particular graph vendor has an index that it can use. But the vendor can optimize that particular step, possibly combine different steps, and then use its own internal optimization capabilities that it has to do the query in a performant manner. Okay, so to continue adding on to our very basic example, we're going to just add an order into this. So we can say select name for manufacturers, and we're going to order these in descending order by name. And so now we have our order step in here, and then we've added a new component into this. We have this by step, and this by is actually a step modulator. So it lives in relation to the step before it. So you say order by, and then the property, and then you can choose whether or not you want to order them in ascending or descending order. And there's a default too. If you just want to go ascending, you can just do by name and leave off that second argument there. So there's various steps you'll see going forward where we're just going to string together a number of these step modulators, and that'll modulate how that step, that parent step, is actually processed. So now if we do a select founded count, so here's a simple group by. We want to do some sort of, say, statistics on our data and grab counts grouped by a particular column. Gremlin, there's a group count step. And so with this group count step, again, we can use this by modulator and say by founded, and we'll get back a hash map. Depending on your, of course, client language, say you're calling this with PHP or something else, that value will be actually deserialized onto your side into whatever data set makes sense for your particular implementation. But in this Java example, it's coming back as a hash map. Okay, so now to looking at queries that deal with just more than one vertex, say something where we're going to actually use these relationships. So in SQL, we have a number of different types of joins, so inner joins and outer joins. So in this example, we have a simple inner join where we're just grabbing all of the manufacturers and then their associated factories. So they're joining on this manufacturer ID. In Gremlin, we have an out step and an in step, and then a few variations on those. And so in this out, we're going to say, just like you would read back probably if you were kind of describing the relationship between the two vertices, we're going to say, go grab me all of the manufacturers, go out their owns edge, so the edges that have the owns label, and then give me back all the vertices, give me back their names. And so that's what you're seeing here. These are all the names of the factories that were out those owns edges. Now, if you were interested in actually some values on the property or on the edges, then you would do out E. So I'm going to go out the edge, owns edge, and then to actually get into the vertex, we'll do an NV. So the out that I showed you before is kind of the shortcut version of this particular step. So if you wanted to filter, say, on particular edge properties, you could say out E owns dot has and filter on the properties, and then go NV to go to the actual vertex. Now this is a two-step hop, so we're going to go out the manufacturers to the factories, and then we're going to, the factories have a made-in edge going into them. So then I say in, made in, and then I'm going to look at the label of all those vertices that come back from that. So in this case, you'll see I get a whole list of trucks back. So the trucks are made in a factory, and a manufacturer owns a factory. And so that's where you can see the directions of those relationships. So manufacturer to factory, and then factory, it has an in edge coming from the trucks. And so that's why it jumps from out to in there. So there's a lot of flexibility there depending on how you want to actually model your data, the directions of edges and things like that. You can see what best fits your problem domain. Now, what I've showed you so far has been an imperative style of querying, which is a little different than what you're used to probably in the SQL world, where in SQL, you could define your joins in a number of different orders, and then all other things being equal, the database optimizer has the ability to reorder your joins based upon things like table statistics. And so what I've shown you so far in the Gremlin world is telling the database, the graph engine, exactly how to perform the query. Go here, then go out to here, then go to here. So there isn't really any reordering happening there. But there is a declarative type option in Gremlin also called this match step. And so this match step allows you to embed these sub-traversals inside of it. So we have this match, and then you're going to see two traversals here. One that goes out to the factories and then one that goes into the trucks. Now, as this is running, the TinkerPop traversal engine will be optimizing it on the fly, maybe changing the order it's running particular traversals in, and so we'll try to pick the most efficient way to run that query. And so this is a pretty simple example, but you can put together much more complex listings of these sub-traversals where the order may come into play, and this may come up with a more optimal execution plan than if you were to tell it exactly beforehand, go from here to here to here. So those were all interesting but basic queries. I'd like to show a few examples of actually kind of more graphy type queries here. So where we're dealing with things like hierarchies or networks. So just really simple here, we have this example, kind of an expansion of the earlier model. So this is one particular truck. And so this truck now has this hierarchy of parts that are laid out below it. So we have a truck that has a GPS, and then this engine, and the engine's made of different parts. The parts connect to each other, and that's what this shows right here. This is all kind of a hierarchy, but you could also imagine connections going from one level to another. So we'll do a few different queries against this structure. So let's say we wanted to start up at the engine. So we have looked for all the parts that have a part type engine. And now I'm adding in this repeat step. And so this repeat step will run this sub-traversal here, this nested traversal, this out has part multiple times, and then emit the values that it's getting at each step of its run. So this is how you can go through and traverse these different hierarchies. So you'll see, if you remember from the previous, we start with our engine, and then we go down and we're going to run into this first level of parts. We have exhaust manifold, crankshaft, intake manifold, coolant sensor, and then below that, as you get deeper and deeper, you're going to get more vertices back. And so you can see that happening here. Now, if you put the emit before the repeat step, you'll notice on the first example, we didn't actually get the engine, the top level part back in the results, but you can change where you put the emit. And if you want to get that, you can put that before the repeat. So these are all variations on this repeat step. If you only want it to repeat a certain number of times, there's a times modulator that you can add in here. So here we're only going out to that first level. We're going to exhaust manifold, intake manifold, crankshaft. If you want to do more of a do-while approach, you could add this until in. And so in this case, we're going to run until we run into the part type transmission. And so this gives you a lot of flexibility depending on what your data looks like to come up with a query that makes sense for what you're trying to get back. Now, if you're interested in the path information, so what were all the different vertices that were hit during this particular traversal, you can add in this path step, and you'll see here this is just showing the vertex IDs, but it's also possible to modulate that and actually show, say, a particular value in that path. So we have these part types. Now I'm showing, so went from engine to exhaust manifold, engine to intake manifold, et cetera, just down the line here. So this is starting to show you one of the spots where if you were comparing writing queries, say, a recursive CTE or something in SQL versus in the graph world, it might be a better mapping to what you're doing if you're writing Gremlin here versus a SQL variant when you're dealing with these different paths. Okay, so last topic, very briefly here, I just at least wanted to touch on this because this is a really interesting and exciting area that the TinkerPop tools have capabilities in. And so this graph analytics with Gremlin, and then specifically we'll talk about SparkGraphComputer here. But so when I say OLAP in the graph TinkerPop world, it's kind of traditionally meant queries that are probably being run against either the whole graph or a large portion of a graph. So these aren't, think not real-time type queries. This isn't something that could happen in under a second. This is something that's going to say, if you're doing a page rank or something and you have a graph with a few billion vertices in it, it may take a while to run this. So in the relational world, of course, the lines are a little more blurred sometimes. So you may be running OLAP queries against the same actual database provider as you do your transactional stuff. So maybe you're using Postgres for OLTP and your OLAP workload. One difference is in the relational world, there's a good chance that you're probably modeling the data differently depending on the approach. So maybe you're doing fact tables and dimension tables for the OLAP side of things, and maybe your OLTP side, that's a more normalized approach that's tuned for low latency transactional execution. On the graph side, usually it's the same graph model either way, so you're not changing how you've laid out your vertices and edges when you're running your OLAP workload. It's probably the same layout as your OLTP workload. But the difference may be, where is that computation happening? And so we'll go through in the next slide some of the different providers that you can use for this OLAP computation. I should say, though, that this is a quickly changing part of TinkerPop, and there is some blurring of lines now even between OLTP and OLAP. And so it is even possible to have a single query where you're in OLAP and OLTP mode kind of going in and out. So I think as time goes on, this will become less obvious potentially to the outside observer, because a lot of this optimization, deciding when to do one approach versus another, will just happen behind the scenes seamlessly. So that's a pretty cool development. So there's two different distributed options that come with Apache TinkerPop for running your large-scale graph queries. There's a SparkGraphComputer and there's a GiraffeGraphComputer. Of course, Spark has their own GraphX, and there's other ways to run graph analytics in a distributed fashion. But TinkerPop can also run on top of these Spark and other frameworks. There's also a single machine implementation for TinkerGraph, and so if you have a large graph but you could fit it, say, in your JVM heap on a single box, you can use this TinkerGraph. And so this is really nice because you get a multi-threaded graph computer on there, and it runs in memory. So for certain data sets, that's probably going to be the fastest way to go, just because you don't have to have this cross-machine communication that you do in the distributed approach. Now, there's different ways you can get your data into and out of these graph computer implementations. So there's a few internal JSON and GraphSon type formats, XML. You can write your own formats, so define your own reader to figure out how to read data in. And so you can place these things in the Hadoop file system, read them out into the graph computer. But you can also read this data in from other graph providers. So say you wanted to run analytics on your DSE graph. So that's just built into the solution, and then it can read data out of the underlying data store into, say, the SparkGraphComputer. So when you're doing OLAP queries, there's two options. One is you can actually just write your OLAP queries using Gremlin. And so the majority of your Gremlin queries will work in OLTP or OLAP mode. There's a few caveats there, but again, that's another area where there's a lot of effort that's going into actually kind of bridging that gap, so there's parity between your OLTP and OLAP queries. But it's really cool right now because for many of your queries, if you know how to write Gremlin, you can write OLTP or OLAP Gremlin without really too much of a change between the two of them. The other option is using this traditional kind of vertex-centric programming model, which really, you may have heard about it in relation to, say, Google's Pregel framework or a number of the other graph computing frameworks out there, like Spark's GraphX. They implement this vertex-centric computing model. And so Apache TinkerPop lets you write your own vertex program. So if you want to actually go and write Java code to do your analytics, you can do that. There's a number of programs that actually come with TinkerPop too. So real quick example here. If you were in the Gremlin shell and you wanted to run your SparkGraphComputer against Spark just using the embedded Spark that comes with the Spark plugin, the TinkerPop Spark plugin, you just connect to your graph. So there's some properties inside of that properties file that tell it where to read data from and other things like that. And you'll grab that G, you're grabbing your graph traversal source. In this case, you're saying that I want to execute this with the SparkGraphComputer. And so now we're doing this really simple query here. How many link 8 paths are in this particular data set? The data set that I'm using comes with TinkerPop. It is a Grateful Dead concert data set. Lots of information in there about what songs were played at different concerts and things like that. And so there's not a ton of vertices in there, but there are a lot of paths through the system. And so this is the sort of thing that if you ran it in transactional mode, there'd be a good chance it would run out of memory, potentially blow up, take way too long. But using the graph computing engine, it finishes very quickly. And so in here you can see how many paths this counted in this particular instance. And that happens in, under a minute there. So conclusions and next steps. So if you're interested in learning more about Apache TinkerPop, I would encourage you to go try it out for yourself. There's a few really good options to do that. One is you can go to, as you would probably guess, the Apache TinkerPop website. There's a great beginner's tutorial section on there. I don't have a link on here, but DataStax also has an excellent Gremlin beginners tutorial up on their DataStax Academy site that you can check out. And then lastly, one of the TinkerPop committers, this isn't actually under the TinkerPop, Apache TinkerPop website itself, but one of our committers, Dylan, has created this Gremlin bin site that you can go to. There's a little screenshot on the right. And this gives you a nice, easy online way to go in, load test data sets up, and play with example queries and just kind of get a feel for the language. So that's also a great way to start. Lastly, I'd like to thank all the Apache TinkerPop folks for all the awesome and hard work and many years of effort they put into this. And then you've seen a few little cute TinkerPop characters throughout this presentation. Special thanks goes to Katrina Yim for all that awesome artwork that she has added to the TinkerPop project. So that is all I have. What questions do you guys have?
Thanks, Ted. Any questions from the audience?
Hey, Ted, coming from the RDBMS world, what is it in the graph design that you would ask someone not to do, kind of like stay away from doing something like that? Is there anything that stands out to you?
Yeah, do you mean like if you were trying to model a particular problem in the RDBMS world, like one that wouldn't maybe map very well to a graph database? Is that kind of what you're asking?
Yeah, in the design consideration, you wouldn't want someone to design it this way because, it's for slow things and not ideal for the graph model. What would you, say if I'm designing a patient table or person table, don't put certain things, the way we generally put an RDBMS, right?
Yeah, so I think, if you're looking at it does kind of come again down to probably what sort of querying you're going to do after the fact to read the data out. So one thing, and this is covered pretty well actually in that initial talk that I linked to that some of our other guys did. So they actually went in and they were working with a customer who had modeled a graph database, but actually in a relational database. And so they basically modeled vertices and edges in the relational database. And it turned out actually that even though the data, you could very easily model it as a graph, when they were running their queries against it, they were really pulling back lots of different things just in sort of regular old tabular report type format. And so in that case, it probably made sense more to just go ahead and map it into the relational database. But if you're looking at doing things more where you're really paying attention to what are the relationships between things, are there varying levels of hops between entities? And so it's not like it's a bad thing to do lots of joins necessarily in a relational database. But those sorts of queries, especially when maybe there's not a set number of joins that you may be executing in a particular query, those might map well to, say, using something like Gremlin, where you can more kind of fluently express that just within the language. And so I don't think there's any really like super hard and fast rules when one is better than the other, but probably what I would suggest to do is just kind of think about, okay, what sort of queries am I going to be doing on the read side with this data? And then if I go through and think through how would I express these queries, say in graph or in SQL, what seems to map better to what I need to actually get out of the database?
Okay.
Great question. Anybody else? I mean, I know we're running up to the end of the hour, but happy to stay on if any other questions. All right. Well, good enough, guys. We'll be sending out the recording to the session here. I see some inquiries. We'll get out this content to all the attendees, everybody who signed up. Check back on our website. We'll also have a lot of other graph related content shortly. Some out there already, and a lot more to come. Thank you very much, everybody. Thanks, Ted.
Cool. Thanks.